Hello everyone, this is the fourth addition to the matrix decomposition series, and today we'll be looking at the Gram-Schmidt process in preparation for the QR factorization. This process allows us to take any set of basis vectors in an inner product space and turn them into a orthonormal basis. And what an orthonormal basis is essentially a set of vectors that are number one, mutually orthogonal to each other, and number two, unit vectors or normal vectors. So under the dot product, these vectors become mutually orthogonal like so, where each of them forms a 90-degree angle with the other. And then with the other half of the Gram-Schmidt process, we will normalize these vectors. So in this case, under the dot product, these vectors will have length 1, hence they are unit vectors. The overall procedure will look something like this. We will start off with our set of basis vectors, and we'll begin by setting an initial vector. This vector will stay the same until the very end, right before we normalize all our vectors. The subsequent vectors will be found by subtracting the orthogonal projection of your current vector onto all the previous vectors that you've already put into your orthonormal set. I will define what an orthogonal projection is in a little bit. And then after we do this, we're then good to normalize all our vectors simply by dividing by the norm of the vectors themselves. All right, before we dive into an example, let's quickly look at how the Gram-Schmidt process actually makes orthogonal vectors. So say, for example, we want to make the following vectors orthogonal under the standard dot product. This would mean that these two vectors need to be in a 90-degree angle somehow. One way to do this is to utilize the idea of an orthogonal projection. This can be thought of as how much one vector points in the direction of the other vector. For the dot product, this is equivalent to simply dropping one vector along a perpendicular axis to the other vector. Now, if we subtract away this projection from our vector, then we can guarantee that our new vector doesn't point in the direction of the other vector at all. And that subsequently means that the two vectors are orthogonal to each other or perpendicular to each other. And that's because we know that two vectors that are perpendicular are sort of independent in a way, where they don't point in each other's direction. And that's what we're after. All right, let's jump into an example now. We will be doing the Gram-Schmidt process on these three vectors in R3, and we'll be using the standard dot product as our inner product. Let's begin by letting V1 be our initial vector, and we won't be touching this vector until the very end. Now let's find the second vector in our new basis, simply by subtracting the orthogonal projection of V2 onto V1. Now we have found W2. You can check that W2 is indeed orthogonal to W1 by dotting them and making sure that you get 0. This will help you make sure that you're on the right track. Now moving on to the last vector, W3. For this one, we would need to subtract two orthogonal projections from both W1 and W2. Applying the same formula, we get the following vector. Again, you can check that all three of these vectors are mutually orthogonal by dotting them and making sure that you get 0. Now for the last part of the Gram-Schmidt process, we will simply normalize these vectors by dividing each of them by their norms. Note that the norm used here must be induced from the inner product. So in our case, the norm is simply the square root of the vector dotted with itself. All right, with that we have found the normal basis for R3. And in the next video, we'll be using the Gram-Schmidt process to decompose matrices into the well-known QR decomposition. That's all for today, and I'll see you next time.